Hello, everyone, and welcome to Physics Lab. So this is Lab 7 on projectile motion, and this video will be appropriate for both Physics 206 and 207. There's only one slight difference where Physics 206 will not do the first few questions in the experiment here. Okay, but otherwise the material is basically identical. So let me start off by reminding you what projectile motion is. So to do that, I'm going to go over to the iPad. Okay, so let's say we have an object. It's being launched from some particular height at some speed and at some angle. So I'm going to call this will be my initial launch velocity, v naught. And that vector makes an angle theta with the horizontal. Okay, so we launch a projectile right at some velocity. And what happens? Well, we know it kind of happens, right? If we look at the trajectory here, it's going to do something like this. It'll kind of like rise to a peak and then come back down and hit the ground over here somewhere. So the first thing I would do is, and often you want to do this when you're solving a projectile problem, is find the components of that initial launch velocity. So in other words, find the x component and find the y component of that initial launch velocity. So to do that, if I go to the tip of the vector and I project onto the x-axis, so I draw a perpendicular down to the x-axis, this basically right here is going to be v naught x, right? That's the x component of v. And if I project over to the y-axis, this is going to be v naught y. So this is the y component of that initial launch velocity vector. Okay, now if we think about this, right, let's focus just on the x direction for now. Assuming that there's no air resistance, right, so no air resistance, then that means that there's no forces after the ball leaves the launcher, right? There's no forces acting on the ball in the x direction. If there's no forces acting on the ball in the x direction, that means the acceleration on the x direction is 0, right? Because if the net force is 0, the acceleration must be 0. If the acceleration in the x direction is 0, that means the velocity in the x direction is constant. So whatever initial velocity you had, whatever our v naught x is, that's going to be the same throughout the motion. So I'm going to draw that at several locations. So I'll just draw an arrow the same length. So the velocity, even at the peak here, right, the velocity is going to be the same in the x direction throughout the motion. Okay, what about the y direction? Again, we're assuming the ball is just in the air. So after it leaves the launcher, are there any forces acting on the ball in the y direction? Yes, the gravitational force, right? The force that the earth exerts on the ball, or you could also call it the weight of the ball. So in the y direction, we get this free rise, free fall motion, right? That we've studied many times. So in the y direction, initially I have this large positive velocity in the y. Then here, it'll still be positive, but smaller. Here, still positive, but smaller. At the very peak, there is no y velocity, right? It's 0, just for an instant. It's all in the x. And then after the peak, it's small but negative, then more negative, and so on. So you can think of projectile motion as consisting of two motions. It's constant velocity motion in the x direction and free rise, free fall motion in the y direction. If you put those together, then you get the motion of a projectile. Okay, another important point here is, so this is really a horizontal displacement from, right, the x position when it's launched to when it lands. But it turns out there's a very special horizontal displacement, and it's defined to be from the point of projection, and it was launched right here, to a point on the path that's at the same elevation as the point of projection, which is right here. So that's the key thing. It has to be the same elevation. This horizontal displacement is called the range. And really a big part of our lab is going to be to investigate how the angle of the launch, so how theta, what angle we launch the ball at, how that affects the range, okay, or how the range depends on that angle. All right, now there's a formula for the range, and it depends on several things. So usually we call R the range. It depends on how fast the ball is being launched at, right? That kind of makes sense. In fact, it's V naught, so it's launch speed squared. It depends on the angle, right? Which is what we're interested in this lab. It's a little more complicated. It's sine of 2 theta, right? That's the angle dependence. And it depends on how strong gravity is, right? So it depends on acceleration to gravity, which is G. Okay, so range is going to be V naught squared sine of 2 theta divided by G. And we will use that often today. Okay, so going back to the lab handout. So again, this is, right, the general motion of a projectile where this horizontal displacement is the range. Okay, in terms of the experiment. So the first part of the experiment, and again, this is only for physics 207. Physics 206 does not need to do these initial 4 questions. So during the first part, what we're going to do is sort of a special case. We're going to launch a ball horizontally off of the table. So it's just launched horizontally. So if you think about that, actually, let me go back to the iPad to show you what this looks like. Okay, so in this special case, right, the ball is being launched horizontally off. Let's say this is a table. The ball is being launched horizontally like this. So this is going to be the initial velocity vector. And again, we know what's going to happen. The ball is going to immediately start to fall until it hits the ground. Right? Because immediately gravity is going to be acting on it. We're only interested in what happens right after it leaves the launcher. So basically the questions are going to ask you to sketch the motion. Again, it's going to look something similar to this. And then it asks you whether there's any forces acting on the ball to cause the motion that you just observed. Yes, definitely, right? And we're ignoring air resistance, but there is a force. There's a force in the y direction. It's the gravitational force, right? So there's the weight of the ball is acting on the ball. And then question 4 is sort of interesting. In that case, what you're going to do, let me see if I can draw this out. You're going to drop a ball. So we have these blue launchers, and they're set up so that, let's see if I can draw this. So you have a ball here, and then one that's being launched out this way. So this one is just being dropped. A pin comes out and this one drops. So this one just goes straight down. And the question is, which ball hits first? So when you launch them, right, they leave together. This one is going to go out. This one is going to go straight down. And the question is, which ball hits the ground first? Okay, and you want to kind of think about that. You can probably find this, a simulation of this online or a video of it online. Okay, so then after you're done that, then we're sort of into the main part of the lab. So this is part 4. These are from your lab manual. So we're basically skipping part 3. This is going right to part 4. So the first question that we have to answer is a modified question 8. And basically what we're doing here is we're determining the velocity, that launch velocity of the ball. Okay, so here's the table. Let me explain what's going on in the table here. So first of all, we are going to be able to determine the time that it takes the ball to pass through the photo gate. There's a photo gate attached to the end of the launcher. You should watch my video. I created a video that shows you how I use the equipment to do this lab. So you want to make sure you watch that video. So we know the time, right, that it takes the ball to pass through the photo gate. We know the diameter of the ball, right? In fact, it's going to be 1.90 centimeters. You can just write that in for all three of these. These are just the different angles that we're going to calculate the velocity at. 15 degrees, we're going to set the launcher at 45 degrees and 75 degrees. So the diameter is 1.90 for all of these. The time is the time it takes that diameter of the ball to pass through the photo gate, okay? If you don't have this data, or if you're watching this because you missed lab, make sure you get the data from your lab partners. If for some reason you can't, email me and I can give you some data for this. If we know the diameter of the ball and we know the time it takes the diameter to pass through the photo gate, then if I divide diameter divided by time, that's kind of like delta x over delta t, that should give me a good indication of the velocity of the ball, right? And this is the velocity of the ball right when it leaves the gun. So you're going to calculate, you're just going to do diameter divided by time, calculate the velocity for 15 degrees, the velocity for 45, the velocity for 75. And it should be similar, right? There shouldn't be too much difference here, but we're just going to average these and we're going to call that our launch velocity. So this average velocity is our launch velocity of the ball. It's our V naught. Okay, then the next thing that you have to do, and this is what this large table is here, is for each of these angles, so 15 degrees, 25, 35, 45, 55, 65, 75, we have to measure the range of the ball from when it leaves the launcher to when it hits the landing platform. And remember, we're talking about range. So the landing platform is at the same height as the launcher, right? Because it has to land at the same height. And again, you should be able to get this data from your lab partners. So I just basically have everyone do 3 trials, right, for each of these angles. So you're getting the range for 15 degrees, just three different trials. Hopefully they're fairly close. Then for 25 degrees, 35, and so on. And then the last column here is just the average. So you're going to average these 3 values to get the average range for each of these angles. Okay, and we know intuitively that the range should increase as we increase the angle up to about 45 degrees, right? 45 degrees in theory, if there's no air resistance, should give you the maximum range. And then after that, it'll start decreasing again. Okay, so get that data. If you're watching this because you missed lab, get that data from your lab partners. If not, contact me and I can give you some data for this. Okay, then your next question that you're responsible for is question 10. Here you're going to plot range, so this last column here, versus angle. So angle is on the x-axis, so maybe make a little X to remind you, and range is on the Y, so range versus angle. Now, it turns out, right, again, the optimal angle theory, like the angle at which we have the maximum range theoretically, should be 45 degrees. So this, you can just write 45 degrees. When you do this plot, when you plot range versus angle, you're going to get like a sine wave as a fit. So what you need to do is you need to determine the maximum range and the angle at which it occurred at from your data, from your sine fit. Okay, let me actually do this out on the iPad again, and then I'll show you how to do this actually on Pascal Capstone when you graph it. Okay, so again, for that question 10, you're plotting range which is in centimeters, versus angle, which is in degrees. And we already know when the angle is 0 degrees, the range is 0. And when it's 90 degrees, the range is 0. Okay, think about like if I launch something, horizontally at 0 degrees, immediately the ball starts to fall, right? So it never gets back to the same elevation, so the range must be 0. If I launch it at 90 degrees like this, then the ball goes up, comes back down, and then that horizontal displacement would be 0 again. So at 0 degrees, the range is 0, at 90 degrees, it's 0. In between, it depends on your data, but it'll, it won't be perfect. Let's say it looks like this. It's gonna peak around 45. So what you wanna do is you wanna do a sign fit to the data. So let's say it looks like this. So you want to do a sign fit. And I'll jump on Pascal Capstone and show you how to do this in a minute. And then this question 10 is asking for the maximum range experimental and the angle at which it occurred at, right? Given this data, given this graph. So what we need to do is we really need to find the peak of the curve here. Right? You always want to use your fit. So we want to find the peak of the curve. Now, you could do that with just a ruler, but it's kind of difficult to do. There's a better way of doing it. There's something called a coordinate tool. And it allows you, it has like crosshairs, it allows you to find that value right there, the peak of the curve, and it gives you the X and Y values. But remember, the X in this case is the angle and the Y is the range. So basically you're getting this value right here. This is like your R, right? I'll call it R max experimental. It's my maximum range experimentally, right, for my data. And then I'm getting this value here. So this is like my R max, right? And then this value right here would be like my optimal angle. I'll call it theta optimal experimental. Right, so that's this value. You can just read off those values. So you're finding the peak of your graph to get the maximum range and the angle at which that maximum range occurred at. Okay, let's go back to the handout. Okay, so now question 10 wants you to compare the optimal angle theory, which we know is 45 degrees, and an optimal angle experimental. This is what you just found from that graph, right? This is the angle at which your maximum range occurred at. Hopefully it's close to 45, but it may not be exactly the same. Then you're gonna compare these two by computing the usual percent experimental error. So think of the optimal angle theory to 45 degrees as being the accepted predicted one. So when you compute percent experimental error, divide by the 45. Then question 11 is basically compare the max range. So in order to find the max range theory, you need to compute that, right? But we know the formula for range. It's V naught squared times sine of 2 theta divided by G. But when theta is 45 degrees, because we're assuming the optimal angle is 45 degrees, when theta is 45 degrees, sine of 2 times theta, sine of 2 times 45 is sine of 90. That's just 1. So I don't even have that part in the equation here because I'm just multiplying by 1. So to compute this value, this max range theory, it's simply going to be your launch velocity squared divided by G. Now, what do you use for your launch velocity? That's going to be your average value. Remember, we found the average speed that the ball came out of the gun at. So you want to take that value, square it, and then divide by G, but we're in CGS units, so you have to make sure G is 980, right, centimeters second squared. So take your average velocity squared, divide by 980. That's going to be your max range theory. And then max range experimental is what you found from your graph, right? When you use the coordinate tool. So that R value, when you found the peak, that's going to be your max range experimental. Then again, compare these two by computing the percent experimental error. Okay, let me show you now. Let me jump on Capstone to show you how to do that sign fit and how to use the coordinate tool for this part. Okay, so we're on Capstone. Let me go to classic templates. Let me choose this one. I want create new user enter data. Let's do angle. in degrees. You could just write out degrees, or if you know how to do the degree symbol, there's a way of doing it. If you hold the Alt key down, do 248 on the numpad, it gives you degrees. But if not, just write degrees in, that's fine. And then here I create new user enter data. I want range tab, and that's going to be centimeters. Okay, so I just made up some data. Let's say this is your data. So we know the angle 0, 15, 25, 35, 45, 55, 65, 75, and 90. And then the range at 0, 0. Then let's say at 15, it was 60. Then let's say it was 98. At 25, at 35, it's 116. Then let's say 128. Then 115, 95, 59, 0. Okay. So now I'm going to plot angle on the x-axis, right? Range on the y. Actually, that looks pretty good. Kind of looks like a sine wave, right? The title would just be range. This is angle. I need to get rid of my line connections like I normally do. So I hover over data point, right click, uncheck show connecting lines. And then for the fit for this one, I want to use sine, which is this right here. So sine. And that does a pretty good fit. Okay. Now here's where I need to find the peak. You don't want to use your data point. You want to find the peak of your graph here. After it does the fit, find the peak of your graph and use that information. So here's where we use the coordinate tool. The coordinate tool icon is the one right to the right of the fit one. So right here. So click on this and then just click on the first one, add coordinate tool. Now we need to change one setting here. So we're going to click on it, right click, go to tool properties, go to coordinates, and the snap to pixel distance. Right now, if we move this anywhere near a data point, it jumps to our data point, and we don't want it to jump to our data point because we want to have fine control over it so we can find the peak. So we need to change the snap to pixel distance to a 1. So just change that to a 1 and then hit OK. Now we should be able to move this. So let me click on it again. Oh, it's being fussy. There we go. Actually, I'm going to zoom in again. And now I'm going to move this to the peak of my graph, which is right around there, I'd say. Okay, so now we found what we want, right? So if you look at these coordinates, this 44.68, that's our optimal angle experimental. And the 126.00 is our maximum range experimental, right? Those are our experimental values for the optimal angle and the maximum range, right? That's how you get them. Now, remember, always include your graph in your group lab report. So if you hover over the border here, right click, copy display, you can paste it into your group lab report. And these numbers will still appear. So you'll have those numbers that you need to do your percent error calculations. Okay, so that's how you do the range versus angle graph. All right, now there's one more part to this lab, and it's very similar to what we just did when we looked at the range versus angle, except now you're going to use a simulation to get your data. So you want to go to the simulation. I'll show it to you in a second. And then for these angles, so 0, 25, 30, so a little bit different than the ones we used before. So 25, 35, all the way up to 65. You want to measure the range of the projectile. The other difference is the simulation is done in SI units. So the range is in meters, right? Where we use the regular wooden launcher, that was CGS units, so it was centimeters. So you have to be careful. So this is actually going to be in meters. And then the questions are basically identical. You're going to plot range on the Y, angle on the X, range versus angle. You're going to do a sine fit, and then you're going to use the coordinate tool to find the max range experimental and the optimal angle experimental. Then just like before, I want you to compare the optimal angles, right? So remember, theory is 45, optimal angle experimental you're going to get from the graph. So compare these by computing a percent experimental error. Then the next question is very similar to what we just did, but comparing the ranges now. So max range theory, you have to compute it, you have to calculate it. Now, For the simulation, I'll show you this in a second, we're going to use specific values. We're going to set the launch velocity, initial launch velocity, to be 18. So you just want to plug in 18 here, square it. And then remember, it's CGS units, so gravity is 9.8 meters per second squared. Sorry, it's SI units, so gravity is 9.8 meters per second squared. So it's going to be 18 squared divided by 9.8. That'll be your maximum range theory. That's this value right here. Your max range experimental will come from the graph. When you do the graph and you do the coordinate tool, you'll have that max range experimental. Then you want to just compare these two by computing a percent experimental error. Okay, so let me show you how to get this data. Like, how do you get this data so you can do your plots, do your graphs? So let me go to the simulation. Okay, so here's the simulation. So a couple of things. You want to bring this down to 0. We don't want to launch at any height. We want to launch right at 0 degrees. So bring it all the way down to 0 degrees. The angle you adjust from here, right? So it's at 25 now, then 30, 35, 45, 55, and so on, or whatever angles you're using. In this case, I guess you're using 25, 30, 35, 40, and so on. So that adjusts the angle. To the speed, we're going to set to be 18. So you can just click on this to go to 18. We're going to leave it at 18 meters per second. And then you can launch whatever you want. I think it's set for pumpkin. I'll just change it to cannonball, right? Don't change anything else. Don't add any air resistance or anything like that. So to do the launch, all you have to do is press this red button here. It launches the cannonball. And now we want to measure the range from here to where it landed, right? Like this point right here, like the axis of rotation of the cannon, consider that as where it leaves, right? That's where it leaves the cannon. So that's the initial part. So to do that measurement, use this little tape measure here. So click on this, put the beginning of it at the axis of the cannon, and then this end we can draw out. And then wherever it lands, you can just read off that value. So that would be the range, 25.34 meters, when the angle was 25 degrees. Then you'd increase this to 30 degrees, launch it again, and then measure that range, and so on and so forth, right, for each of the angles. Now, you might find, depending on your computer screen, you might find that it goes like at 45, it might go off the screen. So you might have to like zoom out and then do the measurement. And the measurement will also scale correctly. So you'll still have the correct measurement here, but you may have to zoom out. It just depends on your computer and your computer screen. Okay, so that should give you all the values that you need. So you have all these values now. So now you can do your plot, right? Range on the Y versus angle on the X. Finding the peak of the graph using the coordinate tool, you'll find the optimal angle experimental from the graph. The theory is already 45 degrees. We already know that. So compare those two by computing the error. And then question 2 was with the range, right? So the experimental range comes from the graph. You'll know that from the coordinate tool. Max range theory, you have to compute. But again, the velocity, remember, we set that to be 18. So it's 18 squared divided by 9.8. That's going to be your max range theory. And just compare these two by computing the percent experimental error. So always divide by the theory one when you do error. Consider the theory to be our accepted value. All right, then there's just one last thing I want you guys to do with the simulation. This is the last question here, question 3. So it says, using the simulation, set the bullseye target to be 20 meters from the base of the cannon. Keep the height of the cannon at 0 meters. With the angle at 25 degrees, what speed should the cannonball be fired at to hit the center of the bullseye? And if we increase the angle to 45, what speed do we need to correctly hit the bullseye? So you don't have to show any calculations or anything for this part, but you just have to come up with the correct initial speed to actually hit the bullseye when it's 20 meters away. So let me go back to the simulation one last time and show you that. Okay, so we're going to set, actually here, I'm going to restart this. I want this down at 0. I want to move this target to 20 meters away. Doesn't matter what you launch. I'll just leave the pumpkin there. And so it's at 25 degrees, and then later you're gonna do it at 45, just those two angles. So we have to figure out what the speed, what the V naught is, so that it hits right in the center of the target. So you're just gonna do this by trial and error. Let's say you think it's 24. Let's try that. Nope, that's way too fast, right? Then, okay, I'll bring it down to 12. Let's try that. Nope, that's not enough. And eventually you'll find the correct speed to hit exactly in the center of the target. And then do the same thing with 45 degrees. Okay, you don't, so and on the lab handout or in your lab reports, you're just going to report that speed. That's all you have to do. If you wanted to, you could calculate it. I mean, you could try and calculate using the range formula. Like, you know, the range is 20, you know the angle, so you could calculate what V naught has to be to hit it, right? That's one way of figuring it out, but I just want you to kind of do it by trial and error. Okay, and then that's it. So that's it for the lab on projectile motion. Great, thanks.